is exactly equal to the mole fraction of 1. Okay, but not this one. Okay, so Raoult's law is basically an approximation in that sense. Okay, now we wrote this equation. We wrote it as mu n is basically mu1 star in the gas phase plus RT ln x1, right? Using Raoult's law. I should use this thing. Okay. Alright. Now this is assuming, okay, so then actually we said that this is the behavior for ideal solution. Because we say for ideal solution, if you remember, okay, if I vary the mole fraction, okay, the pressure should be something like this. Okay, it's a linear behavior. Where actually this is P1 star. This is basically pressure versus XO. Clear? Okay. So if the pressure varies as XO, with the mole fraction, okay. So that is the equation, okay. Which means actually it is varying Raoult's law. Okay. It is actually following Raoult's law. Clear? Okay. Now again, Raoult's law is not, why it is not correct, it is very obvious from here. Okay. I am taking P by P star as the mole fraction, not P by the total pressure. Clear? Alright. But we actually gave you a slightly different way of thinking, that if basically with the mole fraction it behaves linearly, then it is Raoult's law. But it is the same thing. Okay. Now think about it. Just like we introduced, okay, the fugacity. Now what was the fugacity thing? If you remember that I had basically mu0 plus RT ln Pi by P0. Okay, and then I said that okay, I do not know the real behavior. Only thing that Pi, instead of Pi, I will introduce a function, which is f. Okay, which is Fi by P0, and then I connected it. Okay. Similarly, I will also make here a kind of ad hoc, okay, comparison. Also, this is for real solution. Okay, where I get basically mu1 in the gas phase. Okay, is mu1 star plus RT ln x1. In the real system, instead of the mole fraction, I'll have another quantity which is known as activity. Clear? Okay. So, in the real solution, mu1 G is equal to mu1 star G plus RT ln A1. Clear? Okay. Now think about it. Up to what point? Okay. This is exact. Up to this point, this is exact. Okay. Why? Because this quantity replacing it by x1 was wrong. Clear? Now, if this is a correct equation, this is also a correct equation. Okay, this is an approximate equation. That's why I'm using this notation. Okay, so actually A1 is equal to P1 by P star. Okay, x1 is approximately equal to P1 by P star, but A1 is actually equal to P1 by P1 star. Okay, so although I have introduced a new function, okay, it's not very like problematic thing. Why? Because you will just measure the vapor pressure of the solvent, a particular solvent. Okay, if there are many solvents, okay, say component 1, okay, and then compare it if that solvent or that constituent were solely present. Okay, and that experiment will directly give you A1 activity. Okay. However, if you use the mole fraction, that will be wrong or erroneous. Okay, as simple as that. So although in the fugacity, when I introduced that thing at the very beginning, I did not know actually how to connect, and then I had to work out what is fugacity. But the concept of activity is very clear. It is just P1 by P1 star. Okay, it's not very surprising thing. Okay. But then the question is, fine, this is an approximation, okay, and this is a reality. Is there any connection between them? Okay. That again, just like for fugacity, we said that okay, the fugacity is kind of like proportional to the pressure, okay, I can also say the activity is proportional to the mole fraction, okay, or the activity and mole fraction ratio I can actually call it as some coefficient, which is now I'll call as activity coefficient. Clear? This is just, I'm making an analogous thing, okay. But I really do not care because I know actually activity is P1 by P1 star, okay, which I can experimentally measure. Okay, clear? Actually, Raoult's law itself is an approximation in some sense. It is of course an approximation, okay, because P1 by P1 star can never be X1, right? All right. So if I now write it, okay, the entire thing, meaning instead of A1, if I had written it as X1 into gamma 1, okay, so the equation becomes something like this: RT ln X1 plus RT ln gamma 1, right? So this is basically your ideal behavior, okay, and that extra part is basically a correction to for the real system, okay. So all I am incorporating is actually hiding inside gamma, okay, because I can calculate the real ideal thing directly using mole fraction, okay. All the difference between the real and the ideal is lying here. So that's why basically people calculate this activity coefficient, okay, which we'll be discussing in electrochemistry part, okay, how to calculate the activity of ions and all this thing, okay. But there actually the most important thing is this gamma, okay. All right. Now again, you can always argue that okay, so this is suppose the real ideal system, okay. How will be the curve for the real system? Okay. Now as I said that, think about it, like if my okay, X1 of the mole, X1 is what? X1 is basically the mole fraction of the constituent 1. Okay. Now if X1 is close to 1, okay, when this thing happens. Okay. X1 close to 1 means what will happen? Think about it. If X1 is close to 1, okay, activity is basically proportional to mole fraction. Okay. Now, basically then, A, or the activity, actually, if X1 goes to 1, like if I am actually going to the pure state, okay, then what will be the value of the activity? Activity is basically then almost equal to the mole fraction itself, but that ratio, gamma, will be close to 1. Okay, so if this thing happens, actually gamma tends to 1. Why? Because, okay, let me just write the activity also. Okay, clear? Okay. So which means instead of pressure, if I actually plot activity versus a mole fraction or something like that. Okay. So let me just plot it. So what I'm plotting is basically the activity versus any constituent. Okay. So when X1 is equal to 1, okay, think about it. Or X1 is close to 1. This is basically the real or the ideal situation. Okay. But when actually X1 is nearly 1, this region, okay, then I'm saying the activity and the X1 are basically same thing. Should be, because it's basically behaving Raoult's law. Okay. Because if you remember the pressure versus that curve, okay, I told you that the real system will be basically merging this region. Okay. So I'll also have a merging thing here. Okay. And at that time, when X1 is perfectly equal to 1, okay, I'll have activity also equal to 1. Activity cannot be more than 1. Which also tells me for a pure system, I should always take the activity to be equal to 1. Okay. Now how will be the deviation? It can have positive and negative deviation. Okay. In the sense like the curve can be like this, deviated. The curve can be like this also. Okay. But however, think about it, when x1 is equal to 0, okay, the other constituents are present, no 1 is present. Okay. Then the activity should be 0. Okay. So it should come back here. But here, when x1 is very low, x1 is very low means actually with respect to 1, the system is very, very non-ideal. Ideal means that region on my right side. Okay. So here it will not merge, it will basically deviate drastically. Okay. Something like here also it will come. Got it. And here when I am going, actually it is basically merging. Clear? That's basically positive and negative deviation. That's what we are discussing. Okay. With respect to activity versus pressure. But I think one of you asked me this question, if I have pressure versus x1 that day when we are plotting it. Similar plots. Okay. But usually, okay, there we see that the vapor pressure will be always lower than this. Why? Because actually it's a mole fraction which is a negative quantity, and that's why it get reduced from the pure solvent's vapor pressure. Okay. Clear? Okay. It can be sometimes positive, I mean in a real system, because actually if you have a okay, so anyone can answer this question. Like what I'm asking is this thing. So this is a different curve, by the way. This is activity versus x1. Okay, only that connection. Okay. A1 is proportional to x1. Something like we said, fugacity is proportional to pressure. Okay. Connected by a fugacity coefficient. Activity is proportional to mole fraction. Connected by the activity coefficient. That thing I'm plotting there. Okay. Now what I'm saying here, do not get confused with the earlier curve. Like a couple of days back we are plotting something like this, right? P versus x1, say something like this, right? There this was the ideal situation, okay. And then of course there was a deviation, right? Now the deviation, okay, what kind of deviation is it? Is it positive or negative? We said always it is negative. We never showed it as a positive. Okay. Why? Because if you remember, okay, we had something like this kind of thing, right? The negative was because if you think, okay, once we have a mixture, okay, there will be always a Gibbs free energy of mixing that will reduce the chemical potential. However, if you now consider very specific interaction, which we talked about when we were discussing azeotropes, okay, generally, if I have say water, I have, okay, and then water is evaporating in a closed container, I'll have some vapor pressure. Clear? Okay, so for pure water, I'll have the vapor pressure is equal to like if very small amount of salt is present. Okay. Now suppose I'm increasing the salt's concentration, say let's say sodium chloride. What will happen if there is a positive interaction? Like sodium ions will be now solvated by water. Now the water molecules will not leave, right? Then there will be further reduction. Okay. So what I'm saying, there is a mixing thing, which is an ideal thing. Okay, Gibbs free energy of mixing. That's why the chemical potential is always lower. It can be further lower, but it can be opposite also. If there is a hydrophobic kind of interaction, and that opposite thing can actually counteract the negative of the mixing, and then you can have a positive deviation. That we did not discuss. We only discussed in the context of azeotrope, but a very different curve. There we are showing the melting point variation, if you remember, right? How with composition the melting point is changing itself, and then we showed that they actually these curves touch each other, which means basically the composition doesn't change when it is boiling. Okay, that's a very different thing. But we did not give you a systematic discussion. Okay, usually we show everything with respect to the ideal behavior, Gibbs free energy of mixing, and then we basically show you what will be the real thing. Okay, because those interactions are very difficult to model, but very specific interaction. I mean, with the scope of this, of course, you can do like atomistic simulation and molecular dynamics and to understand, okay, what are the specific interaction and then sum up. But up to here, where everything is macroscopic description. Okay, we exactly do not know whether it's a positive deviation or a negative deviation. Okay, but all we are saying that so these two are very different curves. Okay, but kind of you can think that this is a has an analogy. Okay, because whatever you are casting as an activity, okay, like AI. So if I see this is, let's look at this equation. This is an exact equation. Okay, what it says is basically if I have a higher activity, okay, if I have a higher chemical potential, I'll have a higher activity. So instead of a chemical potential, activity is a better way to describe. Okay, why? Because as I showed that activity is just pi by p star. It's not very difficult to measure, okay, or quantify. Okay, for ions, okay, due to all these specific interactions, this will be very much deviated. Okay, and not only for ions, like ions is a very different discussion. Like say, for example, let's say if I think about all this freezing point depression, okay, or colligative properties, whatever we study, okay, everywhere we are actually using the mole fraction or the other way of notation. Okay, now you can actually replace everything by activity. Okay, and the only thing is that everywhere you will have an extra piece, which is RTL and gamma. Okay, so I did not show it all these things. So it will be similar equations. Okay, but in those cases it will be significant, because if you remember that if I add a salt, okay, and we said that basically the freezing temperature only the solutions thing gets separated. Okay, and then the solid and the vapor doesn't change. Okay, if the solute is non volatile. And we discussed about this freezing point depression, elevation of the boiling point, all these things. Okay, but those like calculations are not very correct for the solution, because actually if you add salt, actually it will be a huge change. Okay, in the chemical potential, it is not just the mole fraction. Okay, because it doesn't behave ideally if the salt concentration is significant. If it is very low, it will behave, but if it is significant, you cannot actually get the it quantitatively right. Okay. So then you have to actually consider what is the gamma. Okay, that is one thing. Okay. Second thing, all your other, like any other thermodynamic properties, whichever we are discussing. Okay, everything we started dg is bdp minus sdp, that is correct. Okay, plus mu I dni of course for components, that is perfectly correct. Remember that we made a deviation only where we made the ideal gas approximation. Okay. Then we use the fugacity, and similarly here, okay, we are saying that this thing, of course we knew that it cannot be proportional to the mole fractions, okay, but it is proportional to some quantity, and then we are doing basically an analogy, trying to understand what are the relation between activity and the mole fractions. Okay, not only that, when we discuss the chemical potential, okay, and then if you remember that we had something like reaction quotient, right? Which was basically, if you remember, pi by p0, okay, to the power the stoichiometric coefficient. We were writing it probably as mu, right? And the entire basically multiplication, right? For reactants, it will have a natural negative sign, so it will come in the denominator. For products, it will be the numerator. All of you know, like it will be something like, say, ABCD kind of reaction. It will be basically PC by P0 to the power mu C, all these things, okay, divided by PA by P0 to the power mu A, something like that. Okay. There also, we wrote mu as mu0 plus RTL and P. Okay. That's why this is a combination of P by P0. Okay. Ideally, it should be fugacity. Okay, if it is a gas phase reaction. Okay. In a solution phase reaction, usually we connect the P by P0 to concentrations. Okay. But then, actually I should use activities here. Okay, which will be concentration here, all the concentration term which actually we calculated, plus there will be a combination of all the gammas. Clear? Because it is nothing but gamma into the mole fraction. Mole fraction is directly connected to concentration. Clear? So all this formula, whatever we like kind of discovered, right? So all these can be replaced, okay, by the activity coefficient. But a major application of this thing is in electrochemistry. Okay.